previously we did understand the equations derivation process of how F naught varied due to the motion of the observer and the source. Now let's combine the two equations that we grabbed on in the last video. Now let's combine them. The combined effect, however, results into this one. F naught is equal to Fs multiplied by V plus minus V naught over V plus minus Vs. So let's use our common sense right here. What would happen if you increase the denominator? If you ever increase the denominator, the entire ratio would decrease, right? So if an observer, if the source is moving away, if the source is moving away, you would hear a lower frequency sound. So at that point, you're going to give a plus sign. And if the source is moving towards you, you're going to hear a louder noise. That means the frequency will increase. So you're going to give a negative sign right here. All right. What would happen if the numerator ever increases? If the numerator increases, the ratio increases. And if the numerator decreases, the ratio also decreases, right? So therefore, if the observer is trying to move closer to the source, the observer is going to hear a louder sound. That's why we're going to give plus right here. And if the observer moves away to hear a much lower frequency sound, then we're going to give a negative sign right here. All right, to make things easier and visualization easier for you, let's try to make a table for the formula to set up. So in your y-axis, we will be writing here we will be giving 3 columns right here for the motion of the observer and 3 rows for the motion of the source. And we will be using the formula above to demonstrate what in each scenario it would look like. So this here represents stationary observer. Observer moving towards source. Observer moving away from the source. This right here, this side will represent the source motion. So this is going to be stationary source. This will be source moving towards, and this will be source moving away. Now, let's start from this position. If the observer is stationary and the source is stationary, no one is moving nowhere, the frequency of the observer and the frequency of the source will be exactly same. So we can write here that F naught is equal to Fs. However, if the observer is moving towards the source and the source is, however, stationary, that means Vs will be 0. And if the observer is moving towards the source, the observer is moving somewhere, it's going to hear a very loud sound. So the frequency will increase. So remember, if the frequency has to increase, that means the numerator has to increase as well. In this case, we're going to use a plus sign. F naught is equal to Fs. The Fs is held constant in this process. Now, V plus V naught over V. V. Why not Vs? Because the source has been held stationary. Now, what would happen if an observer tries to walk away from a stationary source that's emitting sound? If the observer tries to walk away, it's going to move towards a zone to hear a much lower frequency sound. So in this case, if you want the frequency to be lower, the numerator had to decrease as well. So therefore, F naught will be equal to Fs into V minus V naught over V. All right. Now, what about a source that is moving towards a stationary observer? Now, if a source is moving towards, now the observer is stationary, so V naught will be zero in this case. And if it's moving towards, the observer will hear a high pitched sound, so frequency will increase, which means the denominator has to decrease. That means we're going to use a negative sign in this case. So it's going to be Fs by V over V minus Vs. And if the observer is moving towards and the source is also moving towards, so the numerator will try to increase and the denominator try to decrease, because decreasing denominator increases frequency and increasing numerator also increases frequency. In this case, a blaring sound and you as an observer both are coming very close. So it's obvious that the frequency of the observed the observer will, however, increase. So therefore, it's going to be F naught is equal to Fs into V plus V naught over V minus Vs. Now, the observer is trying to move away. That means the observer wants to decrease the frequency, so the numerator had to decrease. However, the source is trying to move towards it. So in order to move, if the source is moving towards, that means the source would try to increase the observed frequency and the observer will try to decrease the observed frequency. So if the source tries to increase the observed frequency, the negative sign has to be preferred, and the observer wants to decrease the frequency. So in this case, negative sign is preferred as well. So it's going to be F naught will be equal to Fs into V minus V naught over V minus Vs. Now, if the source is moving away and the observer is stationary, then V naught is zero. And if it's moving away, it wants to cause the frequency to be lower, right? If it wants the frequency to be lower, in this case, if you want the frequency to be lower, so the denominator would increase. Therefore, it's going to be F naught will be equal to Fs into V over V plus Vs. If the source is moving towards, as in the source, if the observer is moving towards, as in the observer wants a higher frequency, plus sign is preferred. And if the source is moving away, the source wants to decrease the frequency. So increasing denominator decreases frequency. So the plus sign is again favored. So it's going to be F naught equal to Fs into V plus V naught over V plus Vs. Now, if the source is moving away and the observer is also moving away, that means both of them want to decrease the frequency, the observed frequency. If the numerator has to decrease the frequency, it must choose negative. And if the denominator wants to decrease the frequency, it must choose positive sign. So this will be F naught is equal to Fs over V minus V naught over V plus Vs. All right, now let's look at a question from the question paper of A-level CIE board, from the A-level CIE board, and the year of question is not mentioned because this is a compiled question paper set from the school quiz side. Now, here the first question says, what is meant by the frequency of a progressive wave? The frequency of a progressive wave can be defined as the number of oscillations, the number of oscillations per unit time. If you write this, you will be gaining 1 mark. But in order to get 2 marks, since the question doesn't only refer us or is only asking us the question about frequency, because it said that what is meant by the frequency of a progressive wave. So you have to say the number of oscillation per unit time of a source or of a particle passing a fixed point. Now, let's look at the question right below. A cathode ray oscilloscope is used to determine the frequency of the sound emitted by the loudspeaker. The trace produced on the screen of the CRO is shown in the figure. The time-based setting is given, show that the frequency of the sound wave is 1600 hertz. Now, what we're going to do here is we're going to find the equilibrium line, and that's right here. The equilibrium line is right here. And 5 small boxes represent 1 centimeter. And in order to find out frequency is basically number of oscillations per unit time. And time period has a formula for CRO. It's easier to use this formula. I usually use this formula. Time period is equal to time base setting multiplied by number of boxes. Now, what's the time base setting right here? It's 250 microsecond. So it's 250 microsecond multiplied by how much time does it take for one complete oscillation to actually form? If you note that from, let's say if you are suggesting from this point and you're going up till this point, this is going to be 1, 2, 3, 4, 5. This is 1 centimeter. 1, 2, 3, 4, 5. This is another 2 centimeter, and this is 1, 2, 3. This is point. This could be determined as 0.5 centimeters. So I can say that the number of boxes for one complete oscillation is 2.5 centimeter. So 2.5 centimeter, and this is microsecond per centimeter. So centimeter is canceled out. So 250 into 2.5 gives me exactly 625 microsecond. Now I need to convert the microsecond to second. That's 625 multiplied by 10 to the power negative 6. That's second. Now, since we consider one single oscillation, the number of oscillation will be 1. Time period will be 625 into 10 to the power negative 6. This will yield me exactly 1600 hertz, right? Okay. Since we just consume the knowledge about Doppler effect, let's attempt question number C. A loudspeaker B emits sound in all directions. A person attaches the loudspeaker to a string and then swings the loudspeaker at a constant speed in a horizontal circle above his head. An observer standing large distance away from the observer hears sound of maximum frequency. When an observer is standing, that means the observer doesn't have motion. The V naught is 0. And here's a maximum frequency means the observed frequency is high. So therefore, we know that formula is F naught is equal to Fs multiplied by V plus minus V naught over V plus minus Vs. If in this case, the observer is going to hear a maximum frequency sound, then the motion of the source change to the motion to the velocity of the sound has to be minus, because we know that if you decrease the denominator, the numerator increases. And in this case, V naught is 0 because the observer is obviously standing and doesn't have a motion. Hence, in order to find this equation, this for F naught, do we know the F naught right here? Yes, the F naught is exactly given to us 640. And in the above question, we found out the frequency of the source was 1600. So therefore, we can write here that 1640 is equal to 1600 multiplied by speed of sound is 340 or 330 divided by 330 minus Vs. So if you subtract this, Vs is going to be 8.05 meter per second. Hence, this is the answer. All right. Let's move to the next part of the question. The next part of the question says that describe and explain qualitatively the variation in the frequency of the sound heard by the observer. Now, as the question said in the first part of it, at this position, it said that the person attaches the loudspeaker to a string and then swings the loudspeaker at a constant speed in a horizontal circle. So if a person is standing right here and the motion of the sound source is therefore changing like this, once the sound source is close to the observer, the other end it's really far away. So the observer would hear sometimes a higher frequency sound and sometimes a lower frequency sound. If the loudspeaker is moving towards the observer, the observer is going to hear a high frequency sound. If it's moving away, the observer will hear a lower frequency sound. This will repeatedly rise and fall due to the motion of the source. So we will be writing that. So we will be organizing our understanding and writing it here since it says describe and explain. So we can write here that the loudspeaker when moving towards the observer causes the observed frequency to increase and decrease when moving away. Hence, the frequency will repeatedly repetitively it will rise and fall due to the motion of the observer. Right. This is another question from the same question paper booklet, and this question is from the year 2022, May, June 16. Uh, this question here says that describe the Doppler effect. What is exactly Doppler effect? If you want to define Doppler effect, it's a change or difference in the observed frequency when the source is moving relative to the observer. So change in observed frequency when the source is moving to the observer. All right. Now, a distant star is moving away from a stationary observer. State the effect of motion on light observed from the star. So, if a distant star is moving away from a stationary observer, the frequency would of the observed frequency would decrease, and we know that relationship between frequency and wavelength is inverse. So the frequency decreases, the wavelength increases, which means it will be more towards the light will be redshifted. Redshifted means the wavelength has increased. So therefore, we can say that the observed frequency decreases and the observed wavelength increases, making the light to be redshifted. Right. Let's move to the next question. This question says that car travels at a constant speed towards a stationary observer. All right. The horn of the car sounds at a frequency of this. So this is the frequency of the sound source, and that is held constant. The observer hears a frequency of 550 hertz. So the speed of the sound is 340 meter per second in this case. And they said that the observer in this case is stationary. All right, looking at all of these, and it says it two words, uh, let's use the formula. We know that F naught is equal to Fs into V plus minus V naught over V plus minus Vs. Since V naught is 0 and it's moving towards will be plus, and this will be minus. Vs in this case is the motion of the car that we need to find out. V in this case is 340 and 340. Fs is the frequency of the source, and that is 510. And F naught is the observed frequency that is higher than the source, so that's 550. So if you make this subject right here, 550 is equal to 510 multiplied by 340 divided by 340 minus Vs. If you make Vs a subject, you will be gaining a number that is 24.7 meter per second. If you round it off, it will be 25 meter per second. So the car here is traveling at 25 meter per second.
If you guys found this video interactive and informative, please do like my videos and subscribe my channel. Until then, keep learning and keep exploring.